All right, let's do four warm-up problems before we get into somewhat new material. It'll be the last thing in the unit before the exam. So, first things first, if you wanted to make that layers and undo table, please do so, but I'm just going to trust that you guys know how to do this using algebra. But if that layers and undoing table benefits you, be my guest, go for it. So if you did the layers and undoing table, you'd notice that I want to get that radical isolated first. So I'm going to subtract 3 from both sides. And if I subtract 3 on both sides, I'm going to get the square root of 2x minus 3 equaled to 8 minus 3, which is 5. And now I want to undo that radical to get 2x minus 3 outside. I want to get free from that radical prison. So how do you propose that I undo that square root? I'm going to square both sides. So that cancels out. The square and the square root cancel out, leaving me with 2x minus 3 is equal to 5 squared, which is 25. Okay, so now I'm going to do algebra. 2x minus 3 is equal to 25. And now I'm going to add 3 on both sides, knocking out the negative 3. And I'm left with 2x, 25 plus 3 is 28. And then I'm going to divide both sides of the equation by 2. 28 divided by 2 is 14. And if you want to check your work, go for it. It's going to come in handy after the 4 review problems. So if I plug in x equals 14, sorry, that red pencil, I need to put a little bit more force into it. 2 times 14 is going to be 28. Okay, 28 minus 3 is going to be 25. So 3 plus the square root of 25, that's 3 plus 5. 3 plus 5 is 8. And that's the output I wanted all along. So that checks out. So x equals 14 is the true solution to this radical equation. Okay. All right, moving on to problem number 2. The square root of 4x plus 1 minus 5 is equal to 0. Do the layers and undoing table if you so wish. Pause the video if you want to do this independently. Okay, so what do I want to do? I'm going to try to get that radical isolated, so I need to undo that outer layer first. So I'm going to add 5 on both sides. Then, once I add 5 on both sides, I get the square root of 4x plus 1 is equal to 5. Oh, another one where it's 5. So now I'm going to undo that square root by squaring both sides. So let's do that. So on the left side, I get the square root of 4x plus 1 quantity squared is equal to 5 squared. Well, the square root and the square knock each other out, freeing the 4x plus 1. So now 4x plus 1 is equal to 5 squared, which is 25. And now I've got 4x plus 1 is equal to 25. Now it's basic two-step algebra. I'm going to subtract 1 from both sides. That leaves me with 4x is equal to 25 minus 1 is 24. 4x is equal to 24. I'm going to divide both sides of the equation by 4, leaving me with x is equal to positive 6. And I'm going to check my work by plugging in x equals 6 into the original equation. 4 times 6 is 24. 24 plus 1 is 25. The square root of 25 is 5. 5 minus 5 is 0. And is that the output that I wanted? Yes, that's the output that I wanted all along. So that is how I know that I achieved a true statement. When x is equal to 6. Okay. Now, all right, number 3, sorry. Negative 6 times the quantity of x plus 1 to the 2/3 power is equal to negative 24. So now I'm going to try to get these undone. So if you picture the x having layers, first it's being added by 1, then it's being taken to the 2/3 power, and then it's being multiplied by negative 6. So I'm going to undo those layers in reverse. So I'm going to divide both sides of the equation by negative 6. So that negative 6 cancels out with negative 6 over here. And negative 24 divided by negative 6 is going to be positive 4. So that leaves me with x plus 1 quantity to the 2/3 power, okay, is equal to 4. Now, how do I undo that exponent? So what I want to do is undo squaring and cube rooting. So what I'm going to do, to the 2/3 power. So the reciprocal of the 2/3 power is the 3/2 power. After all, I want to undo squaring with square root. I want to undo cube root with cubing. So what better way to do that than by taking it to the 3/2 power on both sides? Now, the radicals knock each other out, leaving me with x plus 1 is equal to 4 to the 3/2 power. Well, let's do 4 to the 3/2 power. The square root of 4 is 2. 2 to the 3rd power is 8. So 4 to the 3/2 power is going to be 8. Now I've got x plus 1 is equal to 8. I'm going to subtract 1 from both sides, getting me x is equal to positive 7. And I'm going to check my work on the side by plugging in x equals 7. I'm going to do 7 plus 1, 8. 8 to the 2/3 power. The cube root of 8 is 2. 2 squared is going to be 4. Negative 6 times positive 4 is negative 24. And is that the output that I wanted? Yes. So that checks out. Okay. All right. Number 4 is a little bit different. It's just a few more layers. So 3 times the quantity of x plus 1 to the 3/5 power. So that x plus 1 is taken to the 3/5 power. Then it's going to be added by 6, and then that's equal to 30. So if I look at this by layers, x is first being added by 1, then taken to the 3/5 power, then it's being multiplied by 3, and then it's added by 6. I'm going to undo those layers in reverse. So first things first, I'm going to try to get that rational exponent isolated. So I'm going to subtract 6 from both sides of the equation. So that knocks out the 6, getting me 3x plus 1 to the 3/5 power is equal to 30 minus 6 is 24. Okay. Now, how do I undo those layers? Well, first, I need to divide that 3 on both sides to get x plus 1 to the 3/5 power isolated. So if I divide both sides of the equation by 3, the 3's kill each other. They get 1 over 1. So now I've got x plus 1 to the 3/5 power is equal to 8. Well, how do I undo those layers? Well, I'm cubing it and I'm 5th rooting it, and I want to cancel that out. So what kills cubing? The cube root. And what kills the 5th root? Taking it to the 5th power. So what I'm going to do on both sides is take the reciprocal, take both sides to the 5/3 power. So that leaves me with x plus 1 is equal to 8 to the 5/3 power. The cube root of 8 is 2. 2 to the 5th power is 32. So x plus 1 is equal to 32. I'm going to subtract 1 from both sides. And that gets me x equals 32 minus 1, which is 31. And that should be our solution if I plug it back in. So I'm going to plug in 31 back in for x. Okay. 31 plus 1 is 32. 32 to the 3/5 power, 5th root of 32 is 2. 2 to the 3rd power is 8. 3 times 8 is 24. And 24 plus 6 is 30, which is the output that I wanted all along. So that checks out. So this should be no problem for you at this point. Okay? Now I want to get into what might be the most confusing part of the unit. It's not that bad, just I'm going to tell you my 11th grade experience with this. So we're solving an equation with multiple I gotta sneeze, hang on. Excuse me. So how to solve an equation with multiple radicals. So when I was in 11th grade, back in the year 2004, 2005, when I had a full head of hair and I was, look at that comb, no, look at that afro. The direction said solve for x, check for extraneous solutions. And I was always very confused because I hated that word. I didn't have that good of a vocabulary, so I was thinking in my head, what does extraneous mean? And so if you look it up in the dictionary, extraneous means it's an adjective meaning it's irrelevant or unrelated to the subject being dealt with. So there's your word of the day calendar. Didn't think that you'd get that in Algebra 2, did you? But it also had this category under the Merriam-Webster dictionary that said in parentheses math. It's being a number obtained in solving an equation that is not a solution of the equation. So when I was in 11th grade, my teacher, I can't really draw, but he had Mr. D. He had a horseshoe haircut. He was balding in the front, and I can't really draw, so I apologize. He called them bogus solutions, so that was easier for us to understand. You remember back when we were doing parabolas, and I used to call them happy face or sad face parabolas. That's why, because it's called a standard parabola versus a reflected parabola, whereas a lot of people could understand happy face or sad face parabolas. But anyway, so he called them bogus solutions, even though the book said check for extraneous solutions. So check for bogus solutions. But the main idea of that is basically you did everything algebraically fine. You followed all the rules. You took your vitamins, you said your prayers, you trained like a Hulkamaniac, but you plugged in those x values and it still doesn't work. So that's the thing. Even if you solved for x, you plug it back in and you say, hey, wait a minute, this doesn't work. So let's do some examples where it does work. Okay. So for example, let's take a look at this. The square root of 2x plus 5 is equal to the square root of x plus 7. Well, in this case, I've got square root equals square root. Knowing what we know, I want to get rid of those square roots. And what gets rid of those square roots? Squaring both sides. And then we go back to algebra. So if I square both sides of the equation, the square root gets knocked out by the square root gets knocked out by the square, so I have standard algebra on left and right. So I've got 2x plus 5 is equal to x plus 7, and now I'm just going to solve for x. Well, go back. I want to solve for x, so I'm going to subtract 1x from both sides. That cancels out. 2x minus 1x is 1x. So 1x plus 5 is equal to 7. Or you know what? Don't even need that 1. So it's x plus 5 is equal to 7. And now I'm going to subtract 5 from both. I got a little ahead of myself. Subtract 5 from both sides. And now x is equal to 2. But wait, the directions say solve for bogus solution. So check to see if it works. So I'm going to say x is equal to 2. Okay? So I'm going to plug in x equals 2 on the left and the right, and hopefully they can agree. So 2 times 2 is 4 plus 5. 2 plus 7 is 9. So 4 plus 5 is 9. Sorry about that. There we go. And that's equal to 3. The square root of 9 is 3. So the left and the right agree when x is equal to 2. Pretty basic problem. I'm going to do another basic problem. The cube root of 8x plus 15 is equal to the cube root of 12x minus 5. So if a square can cancel out the square root, what can cancel out the cube root on both sides? So I'm going to rewrite the problem. But I'm going to cube both sides of the equation and hope that we don't get any that we don't get any bogus solutions. So the cube and the cube root knock each other out, getting me 8x plus 15 is equal to 12x minus 5. And you have a choice. Some people like to solve for x on the left all the time. Some people don't like negative coefficients. So your pick. In this case, if I were to subtract 12x from both sides, I would get negative 4x plus 15 is equal to negative 5. If I were to subtract 8x from both sides, I would get 15 is equal to 4x minus 5. Personally, I'm a person who doesn't like negative coefficients. So if you're a type of person who likes solving for x on the left all the time, go for it. So what I like to do is make sure that my coefficient has a positive. That's just the way I am. So now I've got 15 is equal to 12x minus 8x. That's going to be 4x minus 5. And now how to solve for x. I'm going to add 5 on both sides of the equation. 15 plus 5 is 20. 20 is equal to 4x. And now I'm going to divide both sides of the equation by 4. So then 5 is equal to x. Well, let's take a look at the left and the right side. So I'm going to draw a little divider. So I'm going to check. What was my solution again? Oh yeah, x equals 5. So if I plug in x equals 5, so I'm going to get the cube root of 8 times 5 is 40 plus 15 is equal to the cube root of 12 times 5 would be 60 minus 5. The cube root of 40 plus 15 is, 40 plus 15 is 55. And the cube root of 60 minus 5 is also 55. You plug it in the calculator, you're going to get a decimal because there's no whole number getting cubed that equals 55. But you see what I mean, that the left and the right agree with each other if x is equal to 5. Okay? So I'm going to show you one problem where we do get a bogus solution. So what do you notice about this problem that we haven't seen in the previous two? Well, the radical is on one side and not on the other side. I just want to check really quick. Yeah, we're gonna do not one. We're gonna do two of these problems, and then I'll give you guys more on the next class. Anyway, so let's take a look at problem number 3. So I still want to follow the same strategy. I don't like that radical. I'm trying to solve for x. This radical is ruining my party. So I'm going to rewrite the problem. Square root of 7x plus 15 is equal to x plus 1. but I'm still going to square both sides. Now, if I square the left side, I get the square root getting squared, so that cancels out, leaving me with just 7x plus 15. However, if I square x plus 1, do I literally cancel anything out? No, I just make it bigger, which isn't a bad thing. But remember, we're going to FOIL again. So x plus 1 quantity squared, we're going to FOIL. Let me get a pencil so it's lighter. So I'm going to do x times x, which is going to be x squared. I'm going to do x times 1, which is going to be positive 1x, or positive x, whichever you prefer. I like positive 1x. I'm going to do positive 1 times x, which is also going to be positive 1x. And then positive 1 times positive 1 is going to be positive 1. I'm going to combine the like terms in the middle, and I'm going to get x squared plus 2x plus 1. Nothing really happened on the left side. It's just 7x plus 15. Okay? Oh, man. Quadratic trinomials. Here we go. So now my goal is to get the quadratic trinomial on one side. So remember, quadratics, factoring doesn't leave, factoring doesn't leave, factoring does not leave. I'm going to subtract 7x, and I'm going to subtract 15 from both sides, because that gives me 0 on the left side is equal to x squared. 2x minus 7x is negative 5x. 1 minus 15 is negative 14. Uh-oh, we are back. The x-intercepts of a quadratic function. Remember the factoring quadratic trinomials test? So now, oh man, we need to figure out what two numbers multiply to negative 14 and add to negative 5. Well, you can make that table. It's going to be a positive-negative combination with a stronger negative. In particular, strong negative is going to be negative 7. The weak positive is going to be positive 2. So that's going to be x minus 7, x plus 2. If you chose to write it x plus 2 times x minus 7, you would still get the correct, factored form. But the point is, now we use the zero product principle. Split this up into two equations. Because now x minus 7 equals 0, or x plus 2 equals 0. Now, we just add 7 on both sides. And x is equal to 7. That's one of our solutions. Or x plus 2 equals 0, and I'm going to subtract 2 from both sides. And x is equal to negative 2. And some people literally stop and go, hey, this is one of those problems where it has two solutions. Well, we got to check. Sorry about the roller coaster. So what you literally do is you plug it back in, square root of 7x plus 15 equals x plus 1. And I'm going to do the same thing over here. So I'm going to check my work by plugging in x equals 17, x equals 7 into the first equation. And I'm going to hope that I get a true statement. 7 times 7 is 49, plus 15. 7 plus 1 is 8. 49 plus 15, so if I just make this nice and I make this 50 plus 14, that's going to be square root of 64. And the square root of 64 is equal to 8. That is true. So x equals 7, you're good. But let's try this. So let's say I plug in -2. Seven times -2 is -14 plus 15. That'd be -14 plus 15, which would be square root of 1. Okay, -2 plus 1 is equal to -1, and the square root of 1 is equal to -1. I know what you're thinking. Hey, isn't -1 times -1 equal to +1? We don't count negatives when it's the square root of a positive number. Now, if the question was n squared is equal to 1, then yes, n equals -1 would be valid. But if we're just evaluating the square root, it needs to indicate that there's a negative on the outside for it to be -1. So in this case, we say that is false. So if you want to go back to my 11th grade teacher's words, x equals -2 is what's called a bogus solution. So x equals 7 would be the only solution in the solution set. Okay, just to avoid confusion, I'm going to do one more. So let's say I've got this. The square root of 10x plus 9 is equal to x plus 3. Same thing. I want to get rid of that radical, and it's the square root, so what I do is I'm going to square both sides. So if I square both sides, that knocks out. So now I've got x plus 3 getting squared, so I could just mirror it. X plus 3 is equal to 10x plus 9. And now I'm going to get my pencil so it looks nice and light. X times x is going to be x squared. X times 3 is going to be positive 3x. 3 times x is going to be positive 3x. And 3 times 3 is going to be positive 9. So that means that I'm going to circle the like terms and make this x squared plus 6x plus 9 is equal to 10x plus 9. Now I want to get the quadratic trinomial equal to 0. So what I'm going to do is subtract 10x from both sides, but also I'm going to subtract 9 from both sides. Oh, this is going to be nice. So the 9's cancel out, the 10x cancels out, but also the 9's cancel out here, leaving me with x squared minus 4x is equal to 0. So even though it's not a quadratic trinomial, remember I can take out the GCF. What can I factor out of x squared and negative 4x? I'm going to factor out an x. X times what is x squared? X. X times what is negative 4x? Negative 4. And now using the zero product principle, I'm going to break this up into two cases. Well, on the left side, x is equal to 0. That's very convenient. X is equal to 0. Let's hope it stands true. On the right side of the equation, x minus 4 equals 0. Add 4 on both sides gets me x equals 4. So hopefully both of these work out, but I got to plug my equation back. I got to plug my x values back in to the equation. So I've got x plus 3 is equal to the square root of 10x plus 9. So I'm going to do that on both sides. So I'm going to plug in x equals 0 on the left equation and x equals 4 on the right equation. So 0 plus 3 is equal to 3. 10 times 0 is 0 plus 9. 3 is equal to the square root of 9. Oh, in this case, 3 is equal to the square root of 9. That is true. So 4 plus 3 is 7. That's equal to 10 times 4, which is 40, plus 9. So 7 is equal to the square root of 49. And that is, in fact, true. So this is one of those cases where this one has two solutions because I plug them back in and they're both valid. Okay? Sorry about that. I want to see if we can do this one more time. Okay? Let's do this even simpler. Actually, so you get the idea. X minus 6 is equal to the square root of 3x. I'm going to square both sides. And that gets me x minus 6 times x minus 6. If you want to FOIL this out, go for it. I'm just looking at the clock. So square root of 3x getting squared, that gets canceled out. And if you FOILed this out, you would get x squared minus 12x plus 36 is equal to 3x. Okay, so now comes the fun part. I want to get everything to the left side so the quadratic is equal to 0. So I'm going to subtract 3x. So now I've got x squared minus 15x plus 36 is equal to 0. All right, let's see if I can do this. What two numbers multiply to 36 and add to negative 15? Well, it has to be a negative-negative combination because a negative times a negative is a positive. Two negatives added together form more negative. So let me just test them out. Negative 1, negative 36, no. Negative 2, negative 18, no. Negative 3, negative 12, yes. So that forms x minus 3, x minus 12 is equal to 0. Once again, we've got the zero product principle. And x minus 3 is equal to 0. X minus 12 is equal to 0. So what that means is x can either be 3 or 12. But let's plug it back in and hope it's not lying to us. So now, blank minus 6 is equal to the square root of 3 blank. So I'm going to plug in 3 to the left equation and 12 to the right equation. So 3 minus 6 is negative 3. 3 times 3 is the square root of 9. Technically, if you plug in the square root of 9, you're going to get positive 3. So since negative 3 equals positive 3 in this case, this is bogus. Negative 3 is equal to 3 is not true, so x equals 3 is bogus, extraneous. But I like my 11th grade teacher's version, bogus. 12 minus 6 is 6. 3 times 12 is 36. The positive square root of 36 is 6. So this one is true. The x equals 3 is not true. X equals 12 is true. So the only solution that works is x equals 12. Okay? We'll do more examples on this on the next class.